Saturn's North Pole is home to a giant 20,000-kilometer wide hexagon. It is one of the most iconic features in our solar system, famous enough to even appear on the stamps of several countries, but that doesn't mean it's unique. In 2017, NASA's Juno probe discovered something very similar on our largest gas giant, Jupiter. Now, we've known for decades that Jupiter has giant storms at its poles, but these new discoveries show that they have extremely regular shapes. So regular, in fact, that they shouldn't naturally occur. So why do they? These newly observed polygons are sometimes called mini-hexagons. They are much smaller than the one on Saturn and appear as repeating geometric shapes made of clouds rising from the depths of Jupiter's atmosphere. In total, Juno detected 3 different shapes: hexagons, squares, and pentagons. The sizes of these polygons range from just 300 to 1,000 kilometers across. It is easy to spot them against Jupiter's surface because these clouds rise above the surrounding haze. However, it is not so simple to spot them on Saturn due to the planet's rings. But scientists think that they are there if you know where to look. For example, in this image taken by the Cassini probe, you can see the hexagons flanking what looks like a pentagonal-shaped storm. Scientists believe that both Saturn and Jupiter's polygons are formed in a similar way. But before we talk about that, let's take a closer look at how Juno discovered these tiny cyclones. Juno was launched in August of 2011 and reached Jupiter in 2016 after a 5-year journey. Its main task is to measure the mass of the planet's core. And it does other things too, like taking pictures and investigating Jupiter's atmosphere. Juno takes images of Jupiter's poles during its close flybys, which occur approximately every 40 days. The probe uses its Stellar Reference Unit or Starlink for navigation. This device allows Juno to determine its orientation in space using a grid of 12 reference stars. Scientists use the images taken by the probe's camera together with data from the Starlink to track the movement of Jupiter's storms. The first discovery came in 2017 when Juno spotted an 8-sided polygon near Jupiter's North Pole. Since then, scientists have tracked the movement of these polygons, and it turns out that all of them rotate counterclockwise. The scientists behind the discovery say that this suggests a common mechanism for their formation, but it's not all that's surprising. Both Saturn and Jupiter rotate on their axes in the same direction, so it makes sense that the storms rotate in the same direction as well. Also, most of these storms seem to be no deeper than 3,000 meters below the cloud tops, but some of them could stretch as far as 5,000 meters deep into Jupiter's atmosphere. However, the fact that these storms are geometric doesn't make any sense. Storms typically form due to convection, the exchange of heat between fluids, in this case, Jupiter's atmosphere. Heat from deep inside the planet rises and cools as it reaches the surface. When the air reaches its dew point, the gases condense and form clouds. As the air rises, it forms a cumulus cloud, similar to what happens on Earth. However, Jupiter's atmosphere is very different from Earth's. It is mostly hydrogen and helium, and there is no oxygen for clouds to condense around. Instead, scientists think that the storms are formed by convection currents of ammonia ice crystals. These crystals come in various shapes and sizes depending on atmospheric pressure and temperature. As the rising air cools, the crystals change shape and eventually fall back down. If the falling crystals reach the surface of Jupiter before changing shape again, they remain suspended in the atmosphere and form the observed polygons. This process is similar to how snowflakes form in Earth's atmosphere. But instead of water, they are made of ammonia ice. Of course, this isn't the whole picture since the polygons are highly regular shapes which don't occur naturally. For example, if you mix flour and water and leave it for some time, you get a random assortment of flakes. They may have 6 sides, but they won't form perfect hexagons. If you were to repeat this experiment millions of times over billions of years, the final result would still be random. And it gets worse. If you mix sand and water and leave it for a while, you get a large number of hexagons. You can even create other polygons by slightly altering the mixture. So why do the storms on Jupiter and Saturn form such regular patterns? To answer this question, researchers created computer simulations of convection currents in the atmospheres of gas giants. They also took into account forces like Jupiter's rotation and its equatorial bulge. Their results showed that these factors alone cannot explain the formation of polygonal-shaped storms. Instead, they had to introduce an additional force, a type of friction called a nonlinear drag. This is similar to the friction that occurs in a fluid at high speed. It is nonlinear because the amount of friction depends on the velocity squared. The team believes that this extra friction could be caused by the turbulence of Jupiter's atmosphere. As the storm forms, the friction prevents the flow of matter and causes the rising air currents to arrange themselves into regular shapes. This results in the hexagonal, pentagonal, or square-shaped storms that we observe. Now they need to find out how this friction manifests itself in Jupiter's atmosphere and whether it is possible for these structures to exist stably. They also want to understand why only certain shapes occur. For example, on Earth, you can get a wide variety of crystal shapes from convection currents, including plates and columns. But on Jupiter, you only get hexagons, pentagons, and squares. And they only form under very specific circumstances. Some of the model's shortcomings include the inability to accurately recreate all the details of Jupiter's storms and the lack of high-resolution images. Even so, scientists are quite happy with the results. This is the first model that explains how these polygons form without introducing external factors. The scientists behind the study believe that these structures are more common in the universe than we think. We just haven't found many examples yet. To prove this hypothesis, they plan to analyze the atmospheres of exoplanets with similar atmospheres to Jupiter. If they find anything, it will be quite ironic since we may end up knowing more about storms on other planets than on our own. And speaking of irony, Saturn was thought to be the king of rings, but it turns out that Jupiter also has rings. They are intermediate in complexity, halfway between the more extensive set around Saturn and Neptune and the simpler rings found around Mars, Neptune, and Neptune. The discovery was made by the Juno probe using its stellar reference unit. As the probe passed through Jupiter's rings, the starlight changed, allowing scientists to infer that the rings are opaque rather than transparent. They are probably opaque because of the dust from the disintegration of meteoroids. If you enjoyed this video, you can watch another one about Jupiter's rings or check out the playlist with all our videos about space. Thank you for watching and see you next time.